Okay, welcome everyone to my second lecture on quantum topology. So just to recall, just a reminder from last time, I've done a bit of basic category theory for you. And we had this graphical calculus, those famous Penrose diagrams, and they looked a little bit one-dimensional. So the purpose of the next two lectures is basically to explain how to beef it up into a two-dimensional calculus, because, well, two-dimensional, it will be really nice. Today we won't go all the way to the two-dimensional calculus. We will see some nice two-dimensional diagrams, but we need to get some preliminary started before we can really see two-dimensional diagrams. So let me just jump right into the document. Okay, so as last time, I will just go right through my lecture notes, which you will find down in the description. And well, the topic for today are monoidal categories, right? So basically, I want to motivate the definitions. I will give you lots of examples, and I will give you a hint how graphical calculus should look like for those categories. And as I said, the main question I really would like to answer is this one in the green box here. So what are the right axioms to get a two-dimensional diagrammatic calculus? I should say here that monoidal categories weren't invented to get a two-dimensional diagrammatic calculus. History was the other way around. So monoidal categories were invented to generalize basically what we know from vector spaces. I'm trying to explain that as well, but in the end, it turns out they're actually pretty nice two-dimensional versions of categories, if you want, and two-dimensional versions of mathematics. So if you want to think about classical mathematics as being kind of on the line, right, you can multiply a times b basically from two sides. It's a one-dimensional thing. Monoidal categories will be a kind of two-dimensional picture. In some sense, even a three-dimensional picture. We will see that, but mostly a two-dimensional picture. And my motivating example were those. If you remember last time, we have seen the factors. The factors were kind of the right notion of morphisms between categories, and there were morphisms between functors. And those morphisms between functors were called natural transformations. And they basically look like this, right? So this is a natural transformation. Beta, it's called beta, and it was this collection of maps, basically. So one for each object. So I have a beta x, I have a beta y. And here's another natural transformation. Alpha, it's again the same collection. Well, not the same collection. It's again the collection of morphisms, alpha x and alpha y. And well, it's kind of clear that you can stack them in this direction, so vertically. If I have whatever, I would have a gamma here, and gamma goes well one step further, then it would be kind of easy to stack them together. But you can also stack them horizontally. I call this horizontal composition, right? Keep in mind I want to have something two-dimensional, right? So if I already have a natural or an obvious or an evident whatever vertical composition, there should be a horizontal one as well, which should come natural as well. And as you can see, I can kind of glue those diagrams in the middle, right? And get a new diagram. Not quite. What I really need to do is I kind of take this piece and put it on top of this one, or to the left, or whatever, and I get something like this. And do this the same for all others, right? Let me see if I can make this maybe green. Very good. And then you get. Keep in mind that the natural transformation should be a square. So if I have two squares, both squares have four corners, and I kind of glue the corners together in the way I just highlighted here in colors. Then I get a new square. And the fun is now that the arrows go along as well. So I can glue this arrow and this arrow, because they're both functors, so maps. I can just compose them, get a new one. Now I'm running out of colors. Let's try this one of my favorite ones. Ooh, one of my favorite colors. So I can get this one. And there needs to be some kind of new operation to glue those maps together. And this is exactly this horizontal composition, this monoidal product. So here, I'm not really running out of colors. Whoop. And here you kind of need a new idea what to do. And we will see that not all categories admit this horizontal composition, but if you have one, then this picture should convince you that you kind of get a two-dimensional calculus, right? Two-dimensional calculus. Remember that we have vertical composition, kind of God-given. But let's really get started slowly. There will be some very scary looking definitions soon. So let's try to motivate them. And this is probably how people start. I'm not 100% sure, of course. Category theory and monoidal categories were invented mostly in the 40s, 50s, and 60s of the last century. So I'm not 100% sure what those people thought, but this seems to be very likely. And these are the examples you see in old texts, in standard texts, and whatever. And so keep that in mind. Whenever you see those fancy looking definitions later on, what really matters is that you have the examples in mind. So here's hopefully an example that is sounds reasonable for all of you. I call it a down to earth example. So let's see. So the pair category was completely stupid, right? It was just a tuple of objects, it's a tuple of morphisms, and set was the category of sets. And there is a functor, and I call it, well, tensor product or O times, or this funny symbol, a circle with a cross, right? Like a circled multiplication. It is a multiplication, you will see that. And it's the only thing it does is, well, I use this symbol, but this is basically just saying you take the Cartesian product of x and y. So your new elements are pairs, and you can take the Cartesian product of, oh, so this is a notation I will use, but in this example, it's actually this one. You take the Cartesian product of maps, and that's a new set. You take two sets and you create a new set. It's just a very boring one because it's just a Cartesian product. And as I said, I will always kind of use this notation. I will even make it easier in a second. But kind of what you should think is that whenever I write this symbol here, what I mean is there's a specific functor like this that takes two objects and generates a new object, and it takes two morphisms and generates a new morphisms. In this example, it takes two sets and just takes a Cartesian product, meaning now we have tuples of elements, and it takes two maps and creates a Cartesian product, meaning now we have tuples of maps. So this is kind of a very boring and still very illustrative example. And what you will see is that this functor has some nice properties. The functor, I just write O times, as I said. It's what is called a bifunctor. That basically means it satisfies those two equations. So whenever you take the identities, then you get the identity. But identity x tensor identity y is identity downstairs. Can we see this here in this example? Well, so if you take the identity on the set x and you take the identity on the set y, what is a cross product of them? Well, it's of course the identity on the Cartesian product. That's not very surprising. This is, remember that this, no, that was really bad. My skills are really suck here. As this was just G cross F. Okay, so there is a compatibility condition. So you just think about it like this. Now you have two operations basically on a set. Whenever you have two operations on a set, you would like to have some reasonable compatibility conditions. And this is a compatibility condition here, and it's called the interchange law. And you will see a diagrammatic picture in a second why this is already natural. For now, just accept it. Like GF tensor KH is G tensor K composed with F tensor H. It's comparability between the two operation, uh, composition and tensor product. And this is, as I said, comparability. Compatible. Oh, I should learn to write. Compatible. Okay. Okay. So this factor is not completely random. And I mean, I'm still in this example. You can check those. Well, the first one is pretty clear. You can check the other one easily if you just sit down and write it on your screen or on paper or on your iPad or whatever. So these are two properties your functor has. Maybe in the end you would assume them for a general tensor product, for a general monoidal product functor. Yes, that's what we will do. So keep them in mind. You also observe the following, and it will be kind of crucial for what comes later. This is kind of not really associative. So x tensor y tensor z is not equal to x tensor y tensor z. Why is that? Well, an element in this set, that's a set, it's x cross y cross z, actually looks really like this. It's you first cross y and z, you form a pair, and then you form a pair with x. So, and an element in this set looks the other way around. Right? You first form a pair of x and y, and then you put in a z. But come on, they're not equal, strictly speaking, but they are what we call isomorphic. I mean, obviously they contain the same information, right? Whether I put my brackets first in the second slot or in the first slot, come on, that doesn't really matter, right? However, this is kind of a little slightly tricky difference. They're not equal, they're only isomorphic. Keep that in mind. And already in this easy example, that's what you see. So if you want to think of, and I really would like you to think of the monoidal product as kind of a multiplicative operation on categories. Like you can multiply numbers, then you can multiply categories. Then this multiplicative operation is not quite associative. It's only associative up to some isomorphism, up to some, in this case, up to some rebracketing. Right? In contrast to 3 times brackets. Okay, so 3 times brackets 4 times 5 is of course just really the same as 3 times 4 times 5. But here, this is weaker, right? It's a little bit weaker. It's called weak. Well, it's a little bit weaker. It is called weaker. Okay. Just keep that in mind. It's a slight technicality, but basically what we want is that the tensor product resembles multiplication of numbers on the level of categories. It's not quite the same, but it's good enough for you to just think of it as being the same. I usually just completely ignore those technicalities, and well, up to a certain point you can ignore them. That's what I do, and that's what I propose you should do it as well. And the same, by the way, for this, the second thing you would write down here. You have a unit object, 1 times x equals whatever, 1 times 5. Let me do it as an example. 1 times 5 equals 5 equals 5 times 1. Right? That's what holds for numbers. Here it's again a little bit weaker, so it's not equal, but it's isomorphic. Why? Well, okay, if 1 in this case is a 1 object set, which is just a dot, then yeah, then this element, for instance, here, elements in here would be pairs of a bullet element and an element from X. And of course, you can identify that with an element of X, because bullet is just a stupid dummy, it's a stupid placeholder. Um, but they're not equal, right? Same, so kind of the same idea. Just keep that in mind. A lot of very strange diagrams that you will see in a second are just because associativity and unitality do not hold on the nose, but only up to isomorphism, only up to, in this case, kind of reordering your elements, rebracketing your elements, or whatever. Anyway, this is a really, I can actually fit it on one screen. That's basically the blueprint example. Not quite. So for me, the blueprint example would be the same on vector spaces. It's kind of a linear version of it, where the tensor product is the tensor product of vector spaces, which you might have seen in your life before. It's really exactly the same operation, just k-linear. For now, you can ignore that. We will come back to that later. So I just wrote down, so what I just did in the past, whatever minutes, is I explained to you something you already know, namely there's a Cartesian product operation on sets, and I stressed some properties of this Cartesian product operation. And that's probably what, as I said, what people did 80, 70 years ago, and then they kind of general, well, for vector spaces, you get the same, and then they kind of thought, maybe that generalizes. They had a bigger class of examples, obviously. You just don't look at one example and then, oh yeah, let's generalize that. With the bigger class of examples. But basically, this is kind of the blueprint example I want you to keep in mind. So whenever you're struggling with one of the diagrams that was with anything you see below, remind yourself of sets, and just think about what does this actually mean for sets, and you will see it's not so difficult. Okay, let me just go through the conventions very quickly, because it's extremely cumbersome to always write tensor product on objects. I will just write xy, because it is a multiplication. So xy is on objects. So objects are always in this funny font. This is so, and they're always x, y, z, whatever things. And I just write xy instead of x tensor y. And I would write something like x to the k instead of, x tensor x k times. On morphisms, I still write the tensor product symbol, because I already had a shorthand for morphisms involving the composition. Remember, now we basically have two operations. We have a composition and we have a tensor product. And composition kind of always exists. Categories are built such that morphisms have composition. And tensor product doesn't really make sense in general, but sometimes you have it. Sometimes it's monoidal product. Sometimes you have it, sometimes you don't. And if you have it, you actually can multiply objects. That's why I'm using this notation for objects. Okay, I should at least say it once. So here, what I'm saying here is basically, as you will see, something like a monoidal product is actually a choice of structure. So a category can have many monoidal structures. I'm still extremely lazy, and I just say C is a monoidal category, kind of implicitly assuming that I've chosen the monoidal structure, which is nonsense, because there is no the monoidal structure. There could be a bunch of monoidal structures. Anyway, I'm just super lazy. I'm sorry for that. And also, I'm extremely lazy. I should write something like the unit object in C. I will never do that. I will just write the unit object. Anyway, you will survive. It's not so bad. Just keep it in mind that I'm sometimes really simplifying notations. Okay, so let's try to generalize the example we have just seen, the monoidal product on sets, the Cartesian product on sets. Let's just generalize it. Let's try what we can do. And I say it explicitly, the definition is really a mouthful. It looks extremely horrible, but we will get most of the complications later on. And it's really beautiful. So you have a very long and kind of natural definition, but it's extremely hard to remember. So there will be some axioms, and I never remember how they look like. Um, well, you will see. It's not so hard. If you think about it a little bit, you can recover them. But yeah, you will see. It's a mouthful. So you so a monoidal category is already it's already starts great. A monoidal category is has 6 inputs. Okay. Also, I will only write C and kind of, as I said, implicitly assume that you know what the other symbols mean in that context. And what do we have? We have a category. Okay, yeah. Well, shouldn't be too surprising if I'm talking about a model or a monoidal category. We should have a category. Looks reasonable. Um, we have this bifunctor, which we call a monoidal product. So here's my tensor product. It's exactly like for groups. It does something on objects and does something on morphisms, like any functor, right? And the bifunctor here just means, yeah, well, it goes from C cross C to C. There is this unit object, Uppsala. I'm really bad in doing this. Anyway, there's this unit object, and yeah, that's like your one element in the multiplication. Right? This is your multiplication. This is, I say it again. This just, maybe I shouldn't write this symbol. Maybe I should write corresponds to multiplication. Right. That was a really bad choice of color. I can do that better. Whoosh. Okay. Okay. And this one corresponds to the one object, the unit object, right? Whatever you want to call it, the one. Let me just write this like this. So a monoidal product is, oh, by the way, this is a wrong way of writing the natural numbers. The natural numbers are usually written like this. Boubakian notation, whatever. So this is a multiplication in the natural numbers. This is like the unit object in the natural numbers. Yes, and that's how I would like you to think about it. We're really kind of generalizing multiplication of natural numbers. That's the only thing we really understand as mathematicians, right? Multiplication of natural numbers. Well, and addition. We'll see addition later, by the way. But we are kind of generalizing that to categories. So this is kind of clear. This is kind of my choice of set, and I have an operation on my set, which I call the monoidal product, and I have a neutral element on my set. So looks familiar from basically everything you see in your mathematical life, like groups or rings or whatever. And a set together with an operation. At one point, there needs to be some categorical nonsense going on, and here you go. There's a collection of associators. That is just a bunch of natural isomorphisms for any x, y, and z is an isomorphism with 3 brackets. Remember, this was this kind of funny thing which we've seen upstairs. Associativity doesn't hold on the nose. There is a rebracketing going on. And the same for the unit object. The unit object is only a unit up to isomorphism. And even worse, it's only a unit up to isomorphism from the left, my lambda, and from the right, my rho, with two different isomorphisms. So for each x, you have an isomorphism that removes the one from the left, and it removes and another one that removes one from the right, and they're called unitors. Well, left and right. Wow, that was quite a lot. So I have 5 bullet points. The last bullet point has two kinds of data, a left and a right unitor. So we have six types of data: a category, the first three, so a category, a product on my category, and a unit on my category. So that's, as I said, is very familiar from whatever groups, rings. And that's some categorical nonsense because you have to be careful with those bracketings, right? So I have a collection of isomorphisms which I call associators. They mimic the associativity. Well, they give you the isomorphism corresponding to rebracketing, and you have the collection of unitors. Same, but not for rebracketing, but for getting rid of the unit, basically. Right. So this is the A, B, C in your ring equals A, B, C, and this is the, what is it? 1A equals A, and A1 equals A. And it's just not quite true for K, because it's only true up to isomorphism. That's why you have to choose those two extra points of data. You'll see later that you can kind of ignore them, but for now, they're just sticking around here. And then you want to have some, well, some compatibility conditions. And I will comment on that in a second. You don't remember those diagrams. There's basically all the possible ways of bracketing four elements. And there's, between all of them, is kind of a natural, for instance, from here, you can rebracket using this. So the associator, I said again, is just a rebracketing. It's just not an equality of rebracketing. It could be, but in general, it's not. Could throw in a sign. You will see examples in a second. And there's exactly one associator you can draw between those two bracketings, and that's the one you put here. And the pentagon equality just says that kind of all possible ways of bracketing four elements are the same in some coherent way, right? You take four elements, and if you think about four elements have five ways of bracketing, basically, and these are the vertices, the corners of my pentagon. That's why it's called a pentagon. So here's my pentagon. Drawing a pentagon, by the way, is extremely complicated. I can't do it. This doesn't really look like a pentagon, but I hope you get the point. Whatever. So this is a compatibility condition for the associator, so for bracketings. And we have something similar for the unitors, and it's called the triangle equation. Because, well, why? Because there's a triangle, and these are kind of all the possible ways of how to get rid of a one for two objects. For two objects. There is actually another equality, and it comes from assuming naturality. So these are natural isomorphisms. And if you write down what that means, you actually get another equality, which I want to keep you in mind. The square equality. It looks like this. It doesn't matter what it is. What I want you to remember is that we have oh shit, now I have to draw a pentagon again. So we have a pentagon. Don't like pentagon. No, actually wasn't too bad. We have a pentagon equality, we have a triangle equality, and we have a square equality. That's what I want you to keep in mind. Those three. It doesn't really matter how they look like. If you think about it, what you want to do, and you sit down for a while, you would basically write down the same diagrams. If you get confused, of course, you can just look in my notes where I've written it down, or you can just Google it. Of course, I mean, it's not my invention, right? I mean, this is yeah. Actually, I think this goes back to MacLane in the 60s, or I could be wrong here. I think it's certainly in the 60s. I think it's MacLane. I'm not sure. But anyway, what I want you to keep in mind are those three equalities: pentagon, triangle, square, because you will see them in a second later. When we want to get rid of, when we want to get rid of all this data, we really want just a naive multiplication, and we will see that's actually possible. We have to pay a price, but it's actually possible. Okay. A bunch of data we want to multiply on a category. We have a tensor product. So here's all you need to know. We have a category, we have a tensor product, we have a unit, this is kind of what we have. There are some strange constraints about associativity. Well, not really strange. There are some assumptions about associativity and unitality, and they are kind of captured in those equalities: the pentagon, a triangle, and the square. Okay, just keep that in mind. And the point is, all categories will be strict in some way. And a strict category is where all associative unities are identities, which in the end just means you can forget about all this crap. So let me just copy it. Oh, it was bad. Let me just copy it. So there you go. So this just means, oh shit. Okay, this just means strict here just means that all of these are trivial. In some sense, the strict categories are those where you can forget about all those data and you only have, well, your standard multiplication. So strict, in some sense, I would like to think about it like strict equals good multiplication as in the natural numbers. Sadly, most categories are not strict, or at least it's not clear why they should be. So this is the one we have seen above. Set, tensor product is Cartesian product. The unit object is just a stupid one-dimensional set. It's not strict. It's non-strict. So by the way, non-strict is everything that is where, well, it's the opposite of strict. It's not strict. The linear version of the example is a vect. The tensor product is the usual tensor product. The unit is the ground field. I don't care what my ground field is. Any ground field works, and it's again a non-strict categories. And some funny observation is, if you go to the skeletons, I would like you to think about it maybe for a second. But if you go to the skeletons, then with the same monoidal structures, then all of them are strict. Right? This is a really nice example, but let's go to this one for a second, to this one. So monoid structures on categories are usually far away from being unique. On vect, okay, this is certainly the structure which I would choose on vect all the time, but I don't have to. I have a really stupid, well, a really, I shouldn't say stupid, but a different monoidal structure on vect. Namely, I could take the direct sum as my product, which is a bit weirdish, but it satisfies the same axioms, and you would see that you get a non-strict. I mean, this is not what people do usually, but just keep in mind you have, I mean, remember, modular product should be a product, so you better take the one that resembles the product and not the addition. But you could, it satisfies the same axioms. It's not a good idea, but just keep in mind that there is not a unique structure. Right? That's all I want to keep you in mind. Very good. Good. On diagrammatic categories, it's pretty cool, actually. On diagrammatic categories, so remember we had those categories of tangles. So monoidal product is strict. Very good. And it's just given by putting them together next to each other. So this is my horizontal composition, right? This is horizontal. I already had vertical, so I immediately get a two-dimensional calculus, which is it's pretty amazing, right? I can now take my diagram. Here's my diagram, whatever, and I can stack another diagram on the top. It was this composition, or I can take my diagram. Here's my diagram, and I can stack another diagram next to it, and this is this composition. So now I can kind of build a two-dimensional calculus, right? I can go in both directions, which is really, really nice. And kind of the point was, remember that for categories, there's this notion of a Grothendieck group, which was basically just collapsing, just forgetting the morphisms and collapsing objects to equivalence classes. And now the Grothendieck classes of a monoidal category form a monoid. And if you don't remember what a monoid is, it's a group without inverses. So an example would be, of course, our good old friend, right? The natural numbers. And how does a multiplication work? Well, it's just a tensor product on objects, with one being the unit. And the example to keep in mind is if you do this for finite dimensional vector spaces with being the usual tensor product, then the monoid you get are the natural numbers. People would say finite dimensional vector spaces categorize the natural numbers. And how does it work? Well, you associate k to the n, so an n-dimensional vector space, to its dimension n. And because of dimension, my drawing skills are really horrible, dimension v tensor w equals dimension v dimension w, you see that on the other side you really get the natural numbers, right? People call it a categorification of the natural numbers. I really can't draw the symbol for the natural numbers. So vect is a categorification. So finite dimensional vector space is a categorification of natural numbers. So let me give you an important example, which is very different in flavor than the ones we had before. But it's easy. It's easy. It's very easy, but it's very different. So I just take the category of vec G. So G is just some group, and this is G-graded vector spaces. So G-graded vector spaces in its kind of skeleton form. And it's a pretty simple construction. The objects are just by elements of G. So, but for my client for group here, I have 4 objects. 1, 2, 3, 4. The only morphisms are identities. Okay, that's easy, right? I mean, the only morphisms are identities. 1, 2, 3, 4. So just a very discrete thing. I just put 4 vertices, and there. If I wouldn't even bother to draw the identities, then they would have just 4 vertices, nothing between them. Sounds very silly, and it's even, you can make it even sillier. Well, no, not even sillier. You can beef it up a little bit, but it's still very harmless, because you can define the tensor product, monoidal product on this category, but just mimicking the group multiplication, right? So in this case, well, whatever. Let me do an example. 0, 1, tensor 0, 1 is the object 1, 1. It looks a bit weird, but remember that this is additively written, right? So I kind of add things. So, and home spaces are either trivial or empty. I mean, this is a ridiculously simple category, but another incarnation of the group. I just put the monoidal, the group product into the monoidal structure. We have seen this example where the group was, it just had one object, and morphisms were composition of morphisms were group elements, and compositions of morphisms is group composition. This is different. Now my objects are my group elements, and I multiply them with my tensor product, just as I would multiply them with the group. As a category, this is rather boring. And Uh, and it's not hard to see actually that K0 of this thing. I mean, there's basically nothing I mean, there's almost nothing to say. It's just G itself or whatever. Maybe some, yeah, whatever. It's G itself. I mean, that's not hard. There are K-linear versions, the only different, and I will always use these because I mean, um, some classical idea in mathematics is that whenever you can K-linearize, you should. So let's just do it. It's really the same, right? Instead of having one object and no object, I have the ground field, namely K times this one object, or well, zero, zero vector space. That's the only difference, and it's still strict. Ah, yeah. By the way, this is strict, just because well, tensor product was defined by group multiplication, and group multiplication is associative. So this is strict. Um, it gets a bit trickier. You can beef it up a little bit. I don't want to go too much into details. I want you to read it. There's this remark. Um, Basically, what you can do, there's a classical notion, it's called group cohomology. And you can basically twist the multiplication structure uh, by an element in the by a 3 co-cycle of G. So just remember there's a combinatorial. The only thing you need to know basically is there's a combinatorial or numerical datum, and you can throw in some signs if you want. So explicitly, for example, if G is Z mod 2, then well, the group cohomology is Z2. So you can either throw in no sign, then you get the structure from above, or you can throw in a sign, meaning whenever you kind of go around rebracketing, you throw in a sign. And you get another category, which looks very similar. It has the same objects. This category still has K0 being G, but they're not equivalent as monoidal categories. So this is non-strict and skeletal at the same time. Okay, this is a mouse. This is, if you see this for the first time, it looks a bit scary. It's pretty easy idea. You have a very silly, very easy category. It's just a group. Objects are group elements. Multiplication is group multiplication. And now what you do is, these are called twists. You twist the multiplication structure in a controlled way. That's all you do. And you can't see the difference on the Grothendieck group, but now you're non-strict and skeletal at the same time. But it's skeletal by definition because you have trivial home spaces, so things can't be isomorphic. There is just no home space between them. So this picture is still the same, by the way. So for twist or non-twist, it's just the same picture. The only difference is that you have twisted your multiplication structure. Twist of tensor product. Okay. I know that was a bit complicated. If you think about it, it's not so hard. The point is the kind of the difference between categories and rings, or monoids in this case, is that okay, you have a monoid multiplication and you can't do anything with it. And here you have your category multiplication, and you can still twist it upstairs by kind of forcing associativity to not hold on the nose, but in a controlled way up to some numerical datum. And the numerical datum here is just the group cohomology. It doesn't really matter what it is. You basically, you have a discrete way of twisting things. That's it. And you throw away some signs or rules of unity, something like that, to twist your multiplication in a controlled way. Yes, so if you want to read it, I've kind of summarized what's going on. The point is a group cohomology is built such that those two equalities hold. Right? And remember that that's what we are interested in. Yes, and this remark is just saying, okay, whether I take a group or I take a monoid doesn't really make any difference. So same story goes through for monoids and for groups. Anyway, I want to keep you Anyway, let me wrap up. So we have this funny definition. A lot of data, some non-strictness coming from, because things only hold up to isomorphisms. We have three equalities. We have kind of two different kinds of examples. We have the classical examples, where the skeletons are strict, but the categories itself are not. We have diagrammatic examples. They're just really nice. They're strict on the nose. They are two-dimensional, and this is what I will explain in much more details later on. Probably not today anymore, but later on. And there's a third class of examples, which is a bit weirdish, but you can construct, where is it? You can construct non-strict skeletal categories by kind of twisting the tether product structure. So a good question would be whether we can ignore non-strict monoidal categories, since this is really, really a mouthful. It kind of looks like you just need to go to the skeleton, and that's why I gave you the example above. No, that doesn't quite work. You have skeletal non-strict categories, non-strict monoidal categories. There is a way to do it. I won't discuss it in detail, but I will go there. And basically, what I just said is, oh, well, I'm talking to you now for about an hour, maybe 50 minutes or so. And I told you a lot about associators or non-strictness, and then yet it doesn't matter. That's what I just said. It doesn't matter. Or it only matters up to a certain point. Anyway, let's do some diagrammatics, right? This was a mouthful. Well, let's do some diagrammatics. So Feynman diagrams for monoidal categories. This is how it works. So whenever something, so strictly speaking, it's only for strict monoidal categories. Strictly speaking, it's only for strict monoidal categories. It is only for strict monoidal categories. Strictly speaking. Anyway, it's only for strict monoidal categories. In some sense, it doesn't matter because there will be the strictification theorem. But keep that in mind. If you ever run into the problem that something doesn't work, it might be that you're actually in a non-strict category. And I will do the following. I will write x tensor y as two strings next to each other. So kind of the identity on x and the identity on y. I will have f tensor g, and I will write also put them just next to each other. So this is just putting things next to each other, the horizontal composition. And you remember we had those a label or a coupon notation for morphisms. And this is how the interchange law looks like. So the interchange law, in this case, it's just a hide operation. It's just this operation. Right? It's just a hide operation. So the interchange law, actually, it looks a bit strange, but it's just a very natural topological operation on diagrams, on Feynman diagrams. Pretty nice, and it will turn out to be extremely useful for the diagrammatic calculus in the end. What you can also do is now if you have multiple inputs and multiple outputs, that's exactly what you draw. You have three inputs and you have two outputs. You just have a bigger coupon. Okay, so far so good. There's basically nothing. No, that's actually not true. There's nothing scary about it. Oh no, that's true. Sorry, I'm completely confused now. There's nothing scary about it. It's putting diagrams next to each other. The interchange height now. Remember that Feynman diagrams for categories were just on a line. Now you can put them next to each other. Height change operations, and you have kind of bigger boxes because you can have many input strings. X tensor y tensor z to a to the b. Okay, the only thing you're not allowed yet is to do cups or caps. You just go all the way upstairs. Okay. Yeah. Yeah. I'm going to ignore this remark. Let me just go to the example. because this is kind of a nice example. Um, so this is the empty diagram. So one, always remember that. I'm not going to draw that. This is empty diagram. So what is a morphism actually from one to one? It's just a floating box, right? This is a morphism from, oh, maybe I draw it again. So here's my morphism F, and it goes from one to one. Because I decided to draw one empty, it's kind of a floating thing, and it really just floats around by height interchange law. You can pull it down, you can pull it up, you can pull it to the side, and as long as you don't pass any lines, you can just do whatever you want with it. It's just a floating diagram. So this is actually pretty cool if you think about it. You have a diagrammatic calculus, and in the morphisms of the unit object are floating bubbles, if you want, just like little bubbles in your diagram. Float around from left to right, from bottom to top, as long as you don't cross anything else. In particular, you have this funny thing. Oh, yeah, we'll see it later. No, I don't want to spoil the story. Or yeah, no, I don't. We'll see it later. So keep that in mind. And I will now discuss coherence for monoids for a second. And then just wave my hands and say that the same works if you're a little bit more careful for monoidal categories. And then I will wrap up and we're done. So coherence for monoids, the coherent theorem for monoids. If you have never heard about this, just think about it. Whenever someone tells you the definition of a group, what they usually would write, let's say group, and for monoids it's the same, of course. But the usual will write is this one. Right? This, and that's what they call associativity. Strictly speaking, that's kind of really, really bad. It's a really, really bad definition. What you really should say is, well, you have definition one. That's the one you're usually presented in your first class on groups, rings, more linear algebra, wherever you see it. You have a set, you have a multiplication, you have a unit, okay, and you have this equality. What you really should say is you have a set, you have a multiplication, you have a unit, and you have associativity. And this means not just the threefold bracket, well, the twofold bracketing is the same, but any bracketing is the same. So this is any bracketing, and this is the, this is just what it is, the twofold bracketing. Right? And these are not the same definitions. This is kind of the correct definition. Because that's what you want to do. You want to forget about brackets. So any bracketing should be the same, not just the silly, two-term bracketing. But this is a definition you usually, well, this was, by the way, again, a bad choice of color. So the definition you usually get presented, maybe you've seen this. So bad definition. It's really bad definition because it kinds of, so what you should do is you should use the correct definition, and then you should state this theorem. They're actually equivalent because this is the one you want to use in practice, the blue one, not the green one. The green one is horrible. The green one means you have to check infinitely many bracketings. The blue one is much better. You just have to check the first step of bracketing, basically. But it's kind of the wrong definition. Definition 2 should be the right one, and definition 1 should be the consequence. So the theorem should say the two definitions are equivalent. And the way you prove it works as follows. Maybe you've seen some inductive proof or whatever, but it's pretty easy idea. I would just like to draw those diagrams, those tree-like diagrams. And that should just represent the two ways of bracketing things, right? HGF means I first merge F and G, right? I get GF, and then I merge another H to it, and I get HGF. And this is the other way around. And all this is axiom is saying is that those two pictures are the same, right? So this is what I impose. let me just, because I forgot to say it, obviously definition 2 implies definition 1, right? If all bracketings are the same, then for sure the short ones are the same. So I'm going to argue now that definition 1 implies definition 2. Okay. And the only thing you need to check is that basically, if you have now a bigger diagram, then successively applying just a small step, just putting one leg. So basically, all I do is I pull one leg across, right? That's the only thing I do. If you just do this successively, pulling this leg across, pulling the next leg across, group, then you will see that all bracketings are the same. And this implies that all parentheses, all ways of putting brackets are the same. Okay. It's really, really easy argument, but it's kind of crucial to understand that the right definition is actually definition 2, not the one you usually learn in the first class of group theory or on whatever, rings or whatever. It's just a so well-known fact that the definition 2 and definition 1 are equivalent that people get sloppy and just state definition 1. But actually, there's some kind of argument. The argument looks like this. You have this one-dimensional tree-like thing, and just this little operation, just pulling a leg to the other side, it just implies that you could pull legs from anywhere to anywhere for even bigger tree-like diagrams. And if you think about it for a second, each of these tree-like diagrams presents a way of bracketing of whatever, how many leaves you see down here. Okay, you can also state this a little bit differently. You can also say that you have this CW complex, well, a one-dimensional one, call it a graph, right? So here are the 5 ways of bracketing 4 elements. It's a pentagon. It's a pentagon. As you should know by now, the 5 way of bracketing elements. And there's always one operation. So if I pull this leg, for instance, pull this leg. Ooh, this was bad. I just want to pull this leg to this, and then I get to here. And I hope I've done this correct. I pull this leg to here, and I get to here. I pull this leg to here, and I get to here. And from here to here, I pull this leg to here. Okay, perfect. So this is, and you draw this this dotted edge between them if there's a way to connect them, which I've just shown you. And you call this K4, and you of course have Kn in general, just a huge picture and blah, blah, blah. And all the above theorem actually says if you, so this is CW complex, how do you construct it? I say it again. You put all your trees somewhere and you connect them if there is a way to pull legs. And then you get some connected graph. And all the above is saying is that the graph is connected. In other words, pi 0 of your graph is 0. Pi 0 is just meaning, is it connected or not? That was just a rephrasing of the above. And you'll see exactly the same for monoidal categories, just one dimension higher if you want. Okay, let me repeat because it's important. For groups, for monoids, for rings, for whatever you've ever seen in your life, there are actually 2 definitions. The correct one and the practical one. And you usually see the practical one in your first class on groups or whatever. The practical one is you only need to check associativity for this threefold bracketing here. The correct one is you don't associativity holds for all bracketings. The point is they're equivalent by pulling legs, by constructing those funny CW complexes. That's it. And this is so well known that people forget to make a distinction between definition 1 and definition 2. And I really would like to stress this. Definition 2 is the correct one, not definition 1. The right way of stating it is actually that definition 2 implies definition. Definition 1 implies definition 2. Definition 2 obviously implies definition 1. And kind of what will happen now for monoidal categories is that I've presented to you definition 1. And this is called the coherence theorem for monoids, and it says that definition one implies that all ways of putting brackets are the same. So there should be actually a definition two for monoidal categories as well. And that's what I'm going to do next. And the coherence theorem just says that, yep, both are equivalent. So definition one, the wrong definition, the practical definition, has just a finite number of things to check in some sense, and the correct, it implies just the kind of all bracketings are the same. Okay, so let's run through it. So I don't want to make this rigorous, but basically definition two for monoidal categories just as the same input, blah 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 blah, and I don't want to make this precise because it really is horrible to make it precise, but it's kind of morally speaking clear that kind of everything you can build of associators and uniters in the correct way should commute. So every formal diagram should be commutative. And that's definition two. It should be, should be the right definition. This should be the definition of a monoidal category. Although you always see definition one. And the reason is exactly the coherence theorem. The two definitions are equivalent. The coherence theorem for monoidal categories, sometimes called MacLane's coherence theorem, because in this case, I think it really goes back to MacLane in the 60s, maybe to Benabou for two categories, or for bi-categories also in the 60s, but something like that. And it basically is exactly the same as for monoids, just kind of one level higher. You have correct definition, all bracketings are correct, all bracketings work, and you have a wrong definition, but a practical one, like there are only a finite number of things you need to check, and they are equivalent. And the proof is kind of the same. You build a certain complex, and it's now a little bit more complicated, and a little bit higher, and it's called a Stashev polytope. There's the KNs from before, and they are built out of those things for associativity, and if you would include unitality, they would be built out of triangles as well. And you kind of build a certain complex out of them, representing all bracketings. What have I done here? Where each edge represents a bracketing, and each facet, each line represents an associator, and each facet represents one of those equalities. And what you basically say is, what you basically need to prove is that they are always spheres. So pi 1 of them is trivial. Why do I write 1 here, and why do I write 0 above? So this would be a 1. Whatever. Equals 1. 0 equals 1. Very good statement. Whatever. Again, let me just, I don't want to go into details. The details are horrendous. I really don't want to do it. The main idea is that you just mimic what you know from monoids. Monoidal categories are categorification of monoids, and you mimic it, and you get one dimension higher. In this case, you had a one-dimensional CV complex, a graph, and you check that this is connected. In this case, you get a two-dimensional CV complex, like a sphere-like thing, and you check that this is a sphere. And it's, in this case, everything is built out of the basic operations you have, like leg moving, leg pulling. In this case, everything is built out of the basic operations you have, which are squares, pentagons, and triangles. So you don't see any triangles here because it's just associativity. As I said, for unitality, you would have triangles. But this is brilliant. This is really a brilliant theorem. So it doesn't matter how the proof looks like, but this theorem is brilliant. There are two definitions, again, of a monoidal category. The correct one, where all bracketings are the same, and the wrong one, where you only assume, well, pentagons, squares, and triangles, and they're equivalent. That's pretty good, because then you can kind of forget that you need to check all bracketings. You only need to check pentagons, squares, triangles. Like, again, this is so worthwhile to stress it again, like for a monoid, you only need to ever check that this equality holds, and you don't need to check bracketings of order 507. That would be quite tiresome. So this is really, really good. Um, yeah, I'm kind of running out of time, but let me just say that there, of course, is a definition of what a monoidal functor is. It's a functor between monoidal categories, and it's again the same nonsense. It's you need a little bit of extra data. You need a functor, and because that things won't hold up on the nose, you just have an instead of f tensor f of x tensor f of y being equal to f of x tensor y, there is again a choice um, of an kind of associator like thing, and there's a choice of a uniter like thing, such that the natural equality is hold. In this case, again, built in the same way. You just write down all possible bracketings and hope for the best. And yes, you could show some kind of coherent theorem. In this case, you need a hexagon equation, which looks like this, and you have triangle equations, which looks like this. Yeah, and you can, so don't worry too much about it. It's in the strict sense, which we're going in a second, it's much better anyway. Just keep in mind that there is it's kind of a notion of a weak factor. It's the same kind of for monoidal natural transformation. Okay, and the coherence, a certain set of coherence things. Okay. And the point is, as usual, composition of monoidal functors is a monoidal functor. Composition of monoidal transformations is a monoidal transformations. So you get you get more examples of categories, which we will use throughout. Namely, you get the category of monoidal functors. Oops. The category of monoidal functors. I call it MCAT. Objects are monoidal categories, and morphisms are monoidal functors. That's a subcategory of CAT, because, well, you only consider monoidal functors. And yeah, you could consider this is a category of monoidal categories, and there's also the category of monoidal functors, which I indicate in the usual notation, just putting a tensor product down here. And the funny thing is now that if you have any category and you take its category of endofunctors, then this is actually a strict monoidal category. This is really kind of crucial observation. This is a strict monoidal category. It's kind of the blueprint example of a monoidal category, of a strict monoidal category. So so endofunctors. So these are the compositions of that I showed you above. So the morphisms are no above. Oh, I've spent too much time, as you can already see. This was this one. So the morphisms here are natural transformations, and you have two ways to compose natural transformations: vertically and horizontally. That's exactly what you do. And so let me run you through it. A lot of nonsense. So composing functors is the monoidal product on objects, and the horizontal product of natural transformations is the one I showed you, and the vertical one is the usual one, right? So you have two operations, vertical and horizontal. This one and this one. And this is by definition a strict monoidal. So check all axioms. It is a strict monoidal category because everything is built by compositions, and compositions are strict operations, compositions of factors of monoidal transformations. Let me run you through, okay, a little bit more of terminology. Of course, if you have a monoidal category, you should be worried not whether they're equivalent as categories, you should be worried whether they're equivalent as monoidal categories, which I indicate by a monoidal product, which just means that there is an equivalence, which is a monoidal functor. Here are some examples. Finite dimensional vector space is equivalent to its skeleton as a monoidal category. and some playing around with those funny vector categories. So they're basically never equivalent in some sense. Okay, there are many more examples which I'm not going into, but the point is that any monoidal functor induces a monoid homomorphisms on the Grothendieck group, and that's kind of what you want. If the functor is an equivalence, then your monoids are isomorphic, right? If you have, the only thing I'm saying here is if you have extra structure like a monoidal product or a product on the downstairs, then anything that should be isomorphic should keep the structure in mind. That's all I'm saying. And the monoidal functor is the right notion of transporting one structure to the other without losing too much information. And I leave to you to write down what things like monoidal subcategories are and so on and so on. It's yes, I'm really running out of time, so I should try to wrap up. Let me just say that now you have 4 different versions of opposites. You can reverse, well, it's pretty easy. You have 2 operations and you can just reverse either of them. So you have 4 choices, right? So you can reverse none of them, just plain category. You can reverse the vertical composition, call it the opposite. You can reverse a horizontal composition, then you call it the co, or you can reverse both and they call it the co-opposite category. Okay, just keep in mind that there are 4 different versions. Oh, not the co-opposite. You actually call it the bi-opposite. I'm sorry, but anyway, there are just 4 versions. Okay. The point which I want to wrap up now is I want to compare strict versus non-strict categories. And I'm doing this by defining a right modular category. Okay, the category of right modular endofunctors. Whatever that is, doesn't really matter so much. Here's the formal definition. In the end, the point is this category is a strict monoidal category. Okay, this one is a strict monoidal category. And the point is, well, here's the formal definition. This is the blueprint example, the prototypical example of a strict category. And you will see in a second why. Ooh, I really should learn how to do this in a better way. Prototypical example of a strict category. You'll see in a second why. And this proof looks very short. And actually, if you think about it and you read through the definition, that this whole category is built to be strict. Okay. And the whole point, the thing I want to wrap up now with, I give you some funny diagrammatics and examples in the end, but basically this is now the highlight of today's lecture. Maybe I shouldn't say today, because it might be that you're watching this lecture in whatever, whenever you want watch this lecture. But it's the highlight of this lecture is that you have this mouthful of a definition, remember? And it seems unlikely that strict and non-strict are related in any reasonable way. You have pentagon equations, you have pentagon equations, you have square equations, you have triangle equations. They're all just non-trivial and complicated looking for monoidal categories, and they're trivial and trivial and not very complicated looking because they're trivial for strict monoidal categories. I would just guess there's just no way to compare them. And then this again, I think due to MacLane comes around and says, nope. Nope, they're actually the same. For any monoidal category, there exists a strict monoidal category. which is monoidally equivalent to C. But this is just saying everything I told you about strict versus non-strict in the last, whatever, 75 minutes was just completely unimportant. And I could have just started by telling you about strict categories. This is, but I really like this because it's such a surprising result. That's what I'm trying to say here. And this is called the strictification. And it will mean that I kind of ignore, not always, but I kind of tend to ignore the complicated associators and unitors. So in particular, whenever you have a monoidal category, there's a diagrammatic incarnation where you can use Feynman diagrams that I showed you above, right? Yeah. And that's what I would like to do. So very surprising result. It's called the strictification theorem. Any monoidal category can be strictified. That's basically what it says. You can forget about all associators. You can forget about all unitors. You can forget about pentagon equations. You can forget about triangle equations. Very surprising. For most categories, this means you just go to the skeleton, but I have shown you examples of strict skeleton categories which are not, of strict skeletal categories which are not strict, of skeletal categories which are not strict. So it's not quite going to the skeleton. The trick you would use in general is, what you would show is that you can always choose a strictification to be this funny category I showed you above of right endo functors, of right endo module functors of C. This one. This is a little bit complicated looking definition. Any category, it's a version of Unida lemma. Any category is equivalent to endo functors over itself, basically, in a monoidal way. And this is kind of what I sketch here in the proof. It's not so bad. You just check the axioms. But, well, it's also not super enlightening. The enlightening part is that you can't just go to the skeleton. I showed you this example vec G, right? So also it's certainly fine to think of, I go to the skeleton like from vector spaces to matrices, and then everything is strict. It doesn't quite work in general. The general thing is you should consider a category as kind of endo functors over itself. That's your strictification. Anyway, yeah, so you can basically, well, whatever, more graphical calculus. So we had those Feynman diagrams for strict monoidal categories, and now we know that kind of all categories we will ever see in our life, no, actually all categories, all monoidal categories can be strictified. So in some sense, it's saying that you can always use diagrammatic calculus. And the only axiom you would impose on these diagrams is two diagrams are equivalent if you can scale them, we had this before, or they're related by a planar isotopy which keeps the upwards orientation. And yes, and this basically boils down to checking the interchange law. So the graphical calculus is consistent. Two morphisms are equal if and only if diagrams are related by the relation I just told you. Plus the ones we already know, of course. Oh no, sorry, I have written the ones we already know in this 218. So it's exactly 218. And I really mean planar isotopy. So this is not good. You can't pull out H, right? It's kind of stuck. Planar isotopy. And let me finish by something funny. A diagrammatic proof of things. The diagrammatic proof is trivial. Okay, if you know theorem 2, 3, 4, and if you know that everything can be strictified, the diagrammatic proof is trivial. If you try to write it down by hand, it's a bit more complicated. So I claim that endomorphisms of the unit object is a commutative monoid, and it's a totally silly argument. Endomorphisms, I told you endomorphisms of the unit are just floating boxes, and you can just float them around. You can pull G to the side, then all the way down and F up. and then pull F to here and G to here, and they have swapped order. That's it. You just have two boxes and you just did this operation. That's it. Or to be precise, you did this operation. Very, very silly. And it's a one-line proof. If you know everything about diagrammatics, and if you believe in diagrammatics, and please believe in diagrammatics, because this is my whole point of doing those lectures. We like to have diagrammatics. And you can prove other things like you have commutative actions from the left and from the right. So this is not just a commutative monoid, but it also acts on Hom spaces. And what you do is you just either put it from the left, or oh sorry, this was the wrong one. You put it to the left or you put it to the right. And of course they commute, because I mean, first of all, you check that this is an action. Yeah, okay. Just okay, putting a box next to a box is putting a box next to a box. So this checks, and they commute is just I can pull this up, I can pull this down, and yeah, whatever. I mean, I can pull this down, I can pull this up. And you can do more things like that. And we will see much more diagrammatic calculus. So a lot of arguments just simplify by using diagrammatic calculus. It's kind of an illustrative example to try to prove, let's say, this proposition by hand, like using commutative diagrams and so on. The argument, well, and then you might be convinced that the argument using using floating boxes is much easier, because all you do is just, it's a height change argument, the topological planar isotopy argument. Okay, let me wrap up. What have you learned? We have learned, so this is kind of secretly, this is the main theorem today, together with strictification. So we have learned that there is a notion of multiplying in the monoidal category. And it's a little bit flawed. You have to be careful. You have associativity constraints, you have unitality constraints. But in the end, there's a funny strictification theorem, which tells you you don't need to be careful. You can make everything strict. Maybe I shouldn't. Yeah, okay. You can make everything strict, and this just means you have a diagrammatic calculus of the one we already know. And now it has planar isotopies. So it's already two-dimensional. You have planar isotopies. The only thing you need to remember is that kind of upwards oriented planar isotopies. So you don't have any height proofs. So for instance, you can have floating diagrams and you just float around from left to right. As long as you don't cross anything, you're basically fine. And you can pull your diagram here and now, something like that, and you can pull it straight and all those stuff, and it doesn't really matter as long as you don't cross any. So this checks as long as you don't cross anything, or it's destroy kind of the planar topology of what you have drawn, and you're happy. And this just makes life so much easier. You can prove non-trivial theorems, like this is a commutative monoid, and the proof is you don't even need to. The proof is trivial almost. Diagrammatically, it's just that. You can do more fancy things. I will do much more fancy things later and give you diagrammatic proofs of things you really don't want to write down in commutative diagrams. So what I want to make sure here is that you understand is that this is a really, really powerful language, the language of diagrammatic algebra, or diagrammatic category theory that you will use here. And it's all justified by monoidal categories are a two-dimensional calculus, but you need to strictify them. That was the whole point of today's lecture. And if you want to do some, so exercise, this one might be funny. You might try to prove this bimodule structure diagrammatically. That might be funny. And well, I've written down some other exercise you might want to do. This one is also a diagrammatic one, which might be interesting for you to check. Otherwise, next time will be a lot of fun, because next time we continue with more graphical calculus. So that's it for today. I hope it was an enjoyable lecture, and I see you next time. So bye.